The Knuth-Morris-Pratt algorithm, a story about finding patterns in text without ever going back, and about the small insight that made it possible. The problem is simple to state. Given a big text and a small pattern, find every place the pattern appears. Word search, log grep, DNA analysis. It is one of the oldest problems in computer science. The obvious way, line the pattern up at the start of the text. Compare letter by letter. If everything matches, we found one. If not, slide the pattern one place to the right and try again. It works, but it can be brutally slow. Consider a text of 1,000,000 A's ending in a B and a pattern of 1,000 A's ending in a B. Naive matching compares almost every character at almost every position. That is a billion comparisons. Order in times M. On real workloads, this stalls hard. Here is what KMP noticed. When a mismatch happens, we have already matched the first few characters of the pattern. We already know exactly what those characters were. So, do we really need to start from scratch? Or can we skip ahead using what we have already seen? KMP encodes that skip in a small table called the LPS-array. Longest proper prefix, which is also a suffix. For every position in the pattern, LPS tells you the length of the longest prefix that also appears as a suffix ending there. This is the memory KMP uses. Let us build LPS for the pattern ABABCABAB. For A alone, there is no proper prefix. LPS is 0. For AB, no prefix matches a suffix. 0 again. For ABA, the prefix A matches the suffix A. LPS is 1. Then ABAB, prefix AB matches suffix AB. LPS is 2. Continuing all the way gives us this table. 0, 0, 1, 2, 0, 1, 2, 3, 4. This is our cheat sheet. It says at position 8, 4 characters already form a valid prefix. So if we mismatch here, we do not have to recheck those 4. Now the search phase. We walk the text with pointer I and the pattern with pointer J. On a match, both move forward. On a mismatch, only J moves, and it jumps back to LPS of J minus 1. The text pointer, I never rewinds. Text, ABABD, ABACD, and so on. Pattern aligned at position 0. We match ABAB. At position 4, the text has D, but the pattern expects C. Mismatch. In naive matching, we would shift right by 1 and recheck everything. KMP does something smarter. J was at 4, LPS of 3 is 2, so we set J to 2. The pattern effectively slides right by 2 positions, but we do not recompare anything. The text pointer stays at position 4. We continue from there. That is the KMP move. Skip work using the LPS array. After a few more mismatches and shifts, the pattern eventually aligns at position 10 in the text. Every character matches. J reaches the pattern length. That is a match. We record its position and use LPS again to keep searching for the next occurrence. Here is the whole algorithm in less than 20 lines of Python. 2 functions. Build the LPS table, then walk the text using it. The core is that inner while loop, the LPS lookup that makes everything linear. Time complexity, order n plus m. Space, order m. The text pointer, I moves forward exactly n times. It never goes back. The pattern pointer j can move backward, but only as many times as it moved forward. That is the linear time guarantee. KMP shows up everywhere. Command line grep, editor find and replace, DNA sequence alignment, plagiarism detection, substring queries in databases. Anytime you are searching a small pattern in a big text, some flavor of KMP is doing the work. 4 things to remember. 1. Naive is order nm. KMP is order n plus m. 2. LPS is the memory. 3. The text pointer never rewinds. 4. Whenever you find yourself rechecking work you already did, think KMP. That is the whole idea.